calculate. Okay, so we come to the summary for the chapter, and few comments, few general comments. Steady state is when temperature does not change with time. And steady state in a slab results in a linear temperature profile, whereas steady state in a cylinder is not linear. Conductive thermal resistance for a slab is L over Ka, and thermal resistance of a composite slab can be treated as combination of thermal resistances of individual slabs. Now we also saw that this slab thing can be extended, this idea can be extended to cylindrical layers, or composite cylinders or composite spheres, and like we have conductive thermal resistance, convective resistance is 1 over HA, and constant heat generation in a slab with surface cooling leads to parabolic temperature profile. Okay, now an overview of many different possibilities that is useful to know what types of problems we can solve. So we talked about single layer, and then multiple layers, and then presence of heat generation. Each one we did in slab geometry. Some of them we did in cylindrical geometry, and we did not do in the spherical geometry. So the point is, for multiple layers, even though we did one, I showed that you can do all of these if you simply know the resistances in this case and this case. And then for sphere, even though we didn't do, we should follow the same procedure as we did cylinder, but starting with a spherical coordinate. And then presence of heat generation, we only did this one, but again I expect you to be able to solve these two. So the ones that are in thick circles are the ones we actually did, but the rest of it I expect you to be able to do following the procedure that we did in the ones with the thick red circle. So to help do problem solving in this chapter, let's try to have some sort of a map of the things that we did. So this is a chapter of steady state heat conduction, and we did problems without any heat generation and with heat generation. And then without heat generation, what we did is sort of two types of problem, either single layer, slab, cylinder, or multiple layers. So when it's multiple layers, we do the resistance formulation. So basically we do either single layer or multiple layers using the resistance formulation here. Whereas if things don't match, so let's say for sphere we have not done the single layer, then we have to start from scratch. Or if I'm solving a problem that asks you to derive things from scratch, then you have to start from scratch, and we'll talk about in a second how to do from scratch in a general way. Okay, so those are the two possibilities. Now with heat generation, again same idea, we did the one for slab. Now remember, for slab we did with constant temperature given. That's just one type of condition. If we change the boundary condition to flux or convection, then the solution we did is not going to be valid. So only when it's a temperature given, we can use the solution in text. In other cases, For other boundary condition or for other geometries, we have to do from scratch. So again, two ways. Either things match exactly with what we did, then we can use the solution, or we do from scratch. The same here. Now, um, what is a general approach to doing things from scratch? So I'm repeating some of it. So you take the physical situation and you write a schematic, and then you write the governing equation and you write the boundary condition and you solve. That is the procedure from scratch. Little more details when you try to do schematic, which region. So for example, we did a slab, and over the slab there can be airflow. We are not, our interest is in slab, and we are not interested in these regions. So when you develop a schematic, you make sure that you are only including the region or the domain that is of your interest. And it is always nice to see if there is symmetry. That usually makes life easier. Then we get to the governing equation. So the governing equation, how do we get the governing equation? First, of course, we decide based on the geometry as to whether it's Cartesian, cylindrical, or spherical. So we use the general governing equation. Then we start to simplify things. So if it is 1D, then we drop all other terms other than the dimension that we are interested in. Then the terms, so we have transient term, flow, conduction, and storage. Remember, 4 terms. So we keep only the ones we need. So by doing that, you have the specific governing equation for this problem. Then we get to boundary conditions. And the boundary conditions, first you decide how many. So if you are doing a 1D problem has 2 boundaries. Or if you are doing a cylindrical coordinate, then it's these 2 boundaries. So 2 boundaries means you need 2 conditions. Then the problem description should tell you whether it's temperature given, flux given, or convection. Those are the types of boundary conditions. Okay, and if it's a transient problem, then you also need initial condition, meaning what temperature does it start from. We haven't done transient yet, but we will do it shortly.